Welcome to today's Explainer, where we're going to dive straight into Cambridge Physics Syllabus 9702, along with vital overlaps in the 0625, 0652, 0654, 0972, and 5054 syllabuses. I like to think of myself as your personal robot engineer for physics today, because we are essentially going to program your brain for ultimate exam efficiency. We are constructing a foolproof, automated strategy for mastering the equilibrium of forces and the principle of moments. Look, if you have ever stared at a vector triangle, or maybe a really complex pivot problem with ladders and tension wires, and you just felt your mind go completely blank, you are in exactly the right place. Today, we aren't just looking at the raw physics concepts. We are looking at the exact blueprint of how to communicate your physics knowledge to the examiner. We are talking about automated patterns for common question types, so you can walk into that exam hall, see a moment's question, and instantly trigger the correct analytical sequence without even breaking a sweat.
It is incredibly common to wonder why applying these specific principles to unfamiliar contexts feels so challenging and causes so many students to lose marks. To understand this, let's look at two hypothetical students, Alex and Sam. Now, Alex is the kind of student who overloads every single answer with raw physics facts. If a question asks about a uniform beam in equilibrium, Alex will write down every equation they have ever memorized about forces, completely ignoring the specific analysis the question actually wants. It's a total data dump with zero structure. Then you have Sam. Sam is always rushing against the clock. Sam skips right past the command words in the prompt, entirely missing the subtle difference between state, describe, and explain. So Sam calculates a number, slaps it on the page, and moves on, totally missing out on the explanation marks. We see their flawed answers side by side with red pen marks all the time. The disconnect isn't usually in your baseline knowledge, it's in the application. It's the leap from a neat, sterile classroom example to the messy, real-world data presented in the exam.
To fix this, we are going to follow a clear blueprint today. We'll cover 1. The equilibrium challenge, 2. Core theoretical principles, 3. Systematic problem solving, 4. Critical analysis tools, and 5. Examiner insights and strategy.
Okay, let's jump right into Section 1, the equilibrium challenge, and address the absolute main hurdle students face when encountering these questions. The absolute most crucial point to grasp right away is the method mark strategy. What does this mean? It means you are actively rewarded for your structured reasoning and your process, not just the final number. This completely changes how you should view a physics paper. Many students think of physics as just a giant math test, where you either get the correct numerical answer or you completely fail. But academic benchmarks in Cambridge Physics prioritize your journey to the answer. Command word decoding is a massive part of this. When the examiner writes determined by taking moments, they are explicitly telling you how to earn the method marks. If you just resolve forces instead, even if you somehow get the right final tension, you lose marks. If you correctly identify the pivot point, set up the equilibrium conditions where clockwise moments equal counterclockwise moments, and successfully resolve your vertical and horizontal components of tension, but you make a tiny, silly calculator error at the very end, the method mark strategy is what saves your grade. You are proving your analytical thinking, which is exactly what the examiners are actually grading. You have to program your brain to show the sequence.
Now, let's move to our next section, core theoretical principles, and lay down the foundational concepts required to build that winning process.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so the theoretical architecture of equilibrium rests on precise definitions and causal relationships. This is where we need to introduce the PAL framework. That stands for point, evidence, explanation, and link. Top students use this framework to structure their evidence-based reasoning. Academic benchmarks prioritize analytical depth over superficial breadth, meaning you can't just throw a bunch of random equations at the page like our friend Alex. Your reasoning must be evidence-based. If an object is in equilibrium, your point is that it is stationary or moving at a constant velocity. Your evidence is that the resultant force is zero and the resultant moment about any point is zero. Your explanation details how the upward forces perfectly balance the downward forces, and your link ties it back to the specific context of the question, like explaining why the tension in cable A must be double the tension in cable B. That clear, precise causal relationship is the bedrock of your theoretical framework.
What's really interesting here is that principal examiner reports explicitly highlight the candidates who reference cross-topic connections achieve significantly higher marks overall. The examiners aren't just testing rote memory, they are targeting distinct cognitive domains, specifically your ability to apply and analyze across the whole syllabus.
So a top-tier student doesn't just look at an equilibrium problem in isolation. They integrate it with other syllabus areas. For example, let's say you have a heavy steel beam suspended by two cables. What happens if one of those cables suddenly snaps? Suddenly, you aren't just in equilibrium anymore. You are in kinematics and dynamics. The resultant force is no longer zero. You now have a net torque, which means angular acceleration. You have a net downward force, which means you apply F equals ma. Showing that you understand how equilibrium fits into the broader universe of physics demonstrates incredible analytical depth. It shows the examiner that you truly understand the boundaries of the equilibrium condition.
Building on those concepts, let's move into Section 3, Systematic Problem Solving, and look at the exact technical methodology you must use during the exam.
Systematic processing follows this strict, standardized sequence, which mirrors the logical, structured reasoning that examiners are actively hunting for. Remember our students Alex and Sam from earlier? Let's do a mental rewrite of their answers using this framework. Imagine a 60-second timer going off right now as we transform their messy work. Step 1. Identify key elements. Instead of rushing, Sam needs to stop and highlight the command words and pinpoint the specific forces and pivot points. Step 2. Apply relevant principles. Instead of a data dump, Alex needs to select only the principle of moments. Step 3. Execute the analysis with crystal clear working. This is where those red pen marks turn into green check marks. You draw a clear vector triangle tip to tail, or you write out the sum of clockwise moments equals the sum of counterclockwise moments. Step 4. Verify the results. Does the answer actually make physical sense? Step 5. Present it in the appropriate format with correct SI units. We call this the Physics Success Blueprint. Skipping any of these steps is literally like trying to build a robot without the instruction manual. It might look okay on the outside, but it's going to fall apart the second you test it.
When tackling these specific examination questions, you can also think of this as the deconstruct, solve, evaluate method. You are carefully extracting relevant data and selecting your analytical framework. This is a highly active process. You deconstruct the messy, complicated paragraph they give you into clean, logical steps. You solve it systematically. Then, and this is where A-star students really separate themselves from the pack, you evaluate the evidence quality. You check for reasonableness. Let me give you a classic example. If you calculate that the tension in a tiny thin piece of string holding up a small picture frame is somehow 10 million newtons, your check reasonableness step should instantly trigger an alarm in your brain. It should tell you to go back and look for a misplaced decimal point or a conversion error between grams and kilograms. You don't just leave that impossible number on the page, you make justified corrections.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, now that we have our sequence, let's transition to Section 4, Critical Analysis Tools, and look at the tools needed to evaluate evidence quality.
Welcome to our interactive workshop segment. I want you to treat this like a real exam challenge. We are focusing on superficial breadth versus analytical depth. To hit the required analytical depth, your comparative analysis must identify similarities and differences using clear comparative connectives, rather than just listing basic facts. So here is your challenge. Imagine a flawed sample physics paragraph on your screen comparing two different pivot setups. The paragraph just says, setup A has a force of 10 newtons, setup B has a force of 20 newtons, setup A is in equilibrium. Can you find the flaw? The sentence losing marks is the one that fails to connect the data. Providing a simple list is an example of superficial breadth. The examiner wants depth. You need to use comparative connectives. You should be writing, setup A is in equilibrium because the resultant moment is 0, whereas setup B experiences a net torque in the clockwise direction due to the larger 20 Newton force, causing angular acceleration. You absolutely must support each comparison with direct evidence from the data provided, drawing explicit conclusions about their relative physical effects.
Furthermore, evaluating evidence quality requires you to constantly identify limitations, track underlying assumptions, and test how alternative interpretations affect your final conclusion. This is pure high-level physics thinking. Let's do a speed-writing mental challenge. You have 30 seconds to think of a perfect Peel paragraph. Whenever you construct a model of forces, what are you assuming? If a question tells you a beam is uniform, what does that actually mean for your calculations? It means you are making the assumption that the center of gravity acts exactly through the geometric center of the object. What if the string in the diagram is assumed to be light and inextensible? That is an assumption that means we ignore the mass of the string itself, and we assume the tension is constant throughout. Identifying these assumptions and explicitly stating them when asked shows the examiner you understand the difference between theoretical physics models and real-world messy applications.
It proves you aren't just calculating numbers blindly, you are critically analyzing the parameters of the experiment.
Finally, let's dive into our last section, Examiner Insights and Strategy, to look at direct feedback and warnings straight from the examiner's desk. According to principal examiner reports across multiple syllabus codes, these are the top 3 mistakes students consistently make year after year. This proves that dropping the ball on format, presentation, and context will severely cost you. It is fascinating, and honestly a bit tragic, that the top errors aren't usually a fundamental core misunderstanding of Newton's laws. It's formatting. It's failing to put the final answer in the correct SI units, or it's presenting a vector diagram without clear directional arrows on the lines. If you draw a triangle of forces and forget the arrows, the examiner cannot give you the marks because you haven't shown that the vectors are acting in a closed loop, head to tail, to produce a resultant force of 0. And look at that third point, providing answers not specific to the given context. This is what we call the memorized textbook trap. You give a generic definition of moments instead of referencing the actual ladder leaning against the actual wall mentioned in the prompt. You have to answer the question that is in front of you. And this brilliantly illustrates our ultimate takeaway, combining all of our techniques into one final system. You must show your clear working with correct terminology because method marks are your safety net. This quote directly reflects the reality of the grading room. The examiner is actively looking for ways to give you points, but they cannot give you points for a massive blank space, and they definitely cannot give you points for a magical final answer that just appeared out of nowhere without any visible mathematical journey. This is where our time management matrix comes into play. You need to allocate your time based on the number of marks available. If it's a 4-mark question, you cannot just spend 10 seconds writing down one number. You need to dedicate the time to decode the command word, apply the Peel framework, show the moment equation, show the substitution of your raw numbers, and explicitly show the final calculated result with its unit. That is the 3-rules system that guarantees top marks: command word decoding, Peel framework application, and the time management matrix.
So, the final question is, will you let easily avoidable formatting errors drag down your score? Or will you use this structural blueprint to secure every method mark possible? We've seen today that mastering the equilibrium of forces and the principle of moments is about programming your brain for efficiency. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.